current areas of interest in photography. This is a really big overview. I don't expect you to learn the mathematics here. I want to sort of give you a little bit of a flavor of what's happening. Let me just give you an overview of my overview. I'll start off with talking about ancient stuff like pinhole cameras, which is some of you are playing with photography. You might want to even play with stuff like this. They're sort of interesting, and they actually have come back in a different way in modern photography. Then you get into lenses, and all these things have mathematics in it, and I'm not going to get into lenses because that's semesters and semesters of courses right there. Then, how do you store images? I'll just talk a little bit about that. Then I want to get into a little bit of basic mathematics that you use when you have images, which is related to probability. It's related to linear algebra. Linear algebra is everything in a lot of these, not everything, but a lot in a lot of these things. So if you get a chance and want to do some sort of computational photography in your life, besides just use it, you really want to know linear algebra. Derivatives and Taylor series, things that some of you are seeing or have seen in calculus, or maybe you haven't seen yet. These are really basic concepts in image processing. Integrals, I'll mention what it is, that they're all basic concepts in photography. Integrals are related to averaging and things like that. Then I'll get into things where more modern things, or actually they're not modern, all of them. They're things that people have been doing for a long time, where you take many photographs of some sort and you put them together. So, you've probably done this with your cell phones. Actually, the cell phones are spending billions of dollars on photography because this is something that can distinguish a cell phone. Answering the phone is not so important for a cell phone. Everything else is more important, in particular photography. So they're spending billions of dollars on this stuff. When I go to look up people that I saw at a conference that have been talking about this stuff, all of a sudden they've moved to Google, or they've moved to Apple, or they've moved to Microsoft. They're decimating academia because they're using all of this material. So I'll talk a little bit about putting things together for panoramas, where you have many shots and you put them together and you get a big panorama. You put them together for what they call high dynamic range. What this is about is that light goes from very bright to very dark, and it's very hard to capture that on a camera. Well, you can take several photos and capture it, okay? But there are problems. And talk about focus, where you can actually take things and get everything in focus. But we'll talk about that. And then at the very end, I'll talk about some new developments. For instance, there's this one camera out that you take a picture, one shot, and then afterwards you can focus it wherever you want. Okay? And this is really modern computation that lets you do that. And then I'll talk about another thing where, Flickr, you have all these photos on Flickr, right? Well, what this guy can do, Snavely is his name, he's one of the big ones in this, is he can take the photos, let's say, of people that took the photos of the Empire State Building. Thousands of people took photos of the Empire State Building, maybe hundreds of thousands of people. He can put them together so you get a three-dimensional model of the Empire State Building, and then you can peruse it. Okay? He's now at Google, his thesis advisors at Microsoft, they're all working on these things. So let me start at the beginning. We'll see how far we get. I'll start with the pinhole camera, which is also called the camera obscura. Let's see if I can get this to fill out the screen properly. Okay, let's see if I can do this. Okay, here's a picture of a pinhole camera. I don't know why it's so big. I'll have to try to modify the screen eventually. You just take a box. Can you see this? You take a box, you put a hole in it. Okay, a small hole. And they knew about this in the Middle Ages, all right? Actually, probably before. And whatever image is out there, it gives you an image upside down over here. Okay, there's no glass or anything there, it's just a hole. And the nice thing about this actually is that there's no depth of field problem. If you have a little hole, everything is in focus. The problem is that it's very dark. Question?
So yeah, what if it goes upside down?
Well, if you look at the geometry, and that's where the math comes in here, it's just geometry. If you think light goes in straight lines, what's going to see through this hole, this point up here? You're going to see this down here, right? And you're going to see this up here. So it rotates. Now actually, you see things up, you know, if you have your retina, you see things upside down, right? Well, I went to a lecture once where a guy lived with a camera in front of his eyes, a motion, I don't know what type of camera it was, but it was some camera that he could adjust so it turned everything upside down. Okay? Okay, and he just lived that way for a week, and at the end of a few days, he could exist. You know, he just saw the world right, because you can turn it right side up. In other words, if you could stand on your hands for a week, you'd probably be able to work correctly. Did another experiment where he changed white to black and black to white. He couldn't adjust to that. That seems to be much harder because you take cues from shadows. Does that make sense? And that's the explanation that he gave, at least. And he was bragging. He said, look, he had all these pretty women that were guiding him through all of this. You know, he got funded by the NSF to do this. He said, this is the life. You know, he's trying to say it right away. But anyway, with these pinhole cameras, if you know, if you want to look at images, they have some images here. I'll give you this, but one image I wanted to show you. The largest pinhole, they claim the largest image in a pinhole camera, I don't know what that's an image of, it looks like of a city. They made a little hole in a hangar and used that to make a picture. In other words, you know, they made that into effect, a big box with a little hole. Okay. Now the problem with a pinhole camera is that with a little hole you get very little light. Does that make sense? Mm-hmm. So, oh, I know why this is too big, because I made it very big so I could get this. Okay, so I know how to get it smaller when I want. So in any case, then they started with the concept of putting a lens, you know, showing your camera that you got this big lens, the N90 in the back, you got a big lens. What that does is it gets you much more light, okay, so that you don't, because you want to use the light to put it on some medium. So, you know, when you got lenses, why am I not getting anywhere? Oh, okay. When you get lenses, you know, lenses look like one of these things. All of a sudden you get all sorts of mathematics coming in. I'm not going to talk about this mathematics. You know, basically, you know, you have certain parameters with focal length and this and that, and it gets very complicated. You know, courses and courses on lenses. I'm not interested in that in this course. I don't know that. But the thing about lenses, when you get lenses, let me try to lower the resolution on this. When you get lenses, can you see this? This is on the web. There's a danger of using the web, right? Because who knows, I'm using the web, all of a sudden we get advertisements, right? And for all I know, they'll give something lewd. you never know what you're going to get on the web. And it's, you know, that's why you don't want your son using your computer. You don't know where he's going to go, and then you don't know what you'll get as advertisements, right? Okay. I remember one time, I'm using the web, and all of a sudden I see this lewd, you know, this woman, you know, buxom blonde, you know, so what is this? I don't do that sort of thing. And as I look over to look at the picture, it changes for an advertisement for thinning hair. You know, and I figured they had me, you know. they put a leader, and then you look there, and then they get you with what they want to get you on. So they're very smart about these things. But anyway, if you see this, do you see the difference here? This is the concept of depth of field. It's not so clear. This is in focus. This is not in focus, right? Okay, you've all probably seen this problem. It's either a problem or it's a feature. You know, when photographers have learned to use it as a feature. You take a picture of somebody, you might want to focus on their eyes, or you focus where there's action. You focus on their hands, and everything else is blurry. This is very important, right? So it's both a problem and something to use. But we'll talk about how we can get around it or actually change it at will in more modern concepts. So you get, let me make it bigger again. Okay. And on a camera, you can control the depth of field by making the camera more like a pinhole. If you make the camera more like a pinhole, little, you get more depth of field. If you make it get more light by making it big, you get less depth of field, but you get more light, so you can take a picture in darker situations. So there's this trade-off in cameras in general. But all sorts of inaccuracies pop up. If the lens is too wide, the edges of the lens aren't good. If the lens is too small, if you make it too small, you get what's called diffraction, which messes up your picture. So there's a whole theory about this. Now, once you have light that's falling on something, you have to record it. How do you record it? Okay? Well, artists, oops. Come on. Okay, let me make it small now. Artists, what they did is they took these pinhole cameras. You see what's going on here? They put it on a sheet. Wow. Okay, that's your original photography, right? And then they would paint it. Now, actually,
I thought actually just did it through their own eyes.
Well, not of course. Some artists, you've seen they weren't, but a lot of artists did this. In fact, if you can look this up if you want, but if you look at Vermeer, okay, Vermeer here's an example of a Vermeer.
Oh, okay. Really?
This evidently they think this guy here actually painted the Vermeers by making a setup like this, and he thinks that Vermeer actually used one of these camera obscurers to make his paintings, and he's an amateur, he's not an artist or anything, this guy. He was able to make something that looked very much like a Vermeer using this process. Yeah.
So realism might have started through pinhole camera.
Yeah, well, artists will use anything they can.
Yeah.
The artists are not, it's not like I'll take a vow never to use something mechanical. They'll use anything they can to get their effect. I mean, some of them are very pure. I'm only going to use fountain pens, or something like that. But Vermeer has these things that are the lighting is accurate and beautiful, and this guy can reproduce it as an amateur using.
Could you reproduce Girl in the Pearl? There's a famous painting.
I think actually there's a picture of her in one of. I don't know if he did that one. Okay, but I don't remember. You'd have to read the article. You can look it up.
The lighting on that is like amazing on that.
Yeah, right. I mean, that's the thing. Vermeer is known for amazing color and light renditions, and this guy was able to. That's cats and stuff. That's where I get my advertisements here. I don't have a cat. I never look for cats. I don't know why the cats are on there. All right. Let me get back. Okay. So, then you soon started having, film of some sort. Okay, and I want to talk about film. There's a whole theory of how to work with film that's very mathematical. And if you want to do film photography, read Ansel Adams, if you haven't read him already. Because he has all sorts of theory. You expose one way and then you develop another way. It's moderately mathematical, but I don't want to get into that. Okay, now we're going to start into what I want to talk about is the digital realm, where, let me get one image or something, these images, how do I get this out? Let me see, can I make it smaller? No, that doesn't help me here. How do I get out of this? Here we go. Let's, let me see, let me do that, please. And let me get over to here. Let me put my glasses on, because I can't see now. Put it up. Yeah.
Just one question. So, you said how film cameras work. Do Polaroid cameras work the same way? Or is it
No,
different?
they
Like,
have,
because they, like, burning an image of what they capture.
they put it, the thing that Polaroid cameras did is they gave you an image quickly, just like you get with the digital camera. Okay, so they had all sorts of papers and chemicals there that when you exposed it to light, it started developing. And then you would take it out and get your image quickly.
Right.
So they're really fantastic. And actually, some artists still use Polaroids. I know Terry Towery got a hold of like an 8x10 Polaroid camera he could rent, which he could then take, their 8x10 negative, and he played around with that. You get different types of tonalities with that. So film will give you a little different tonality. Okay. And so that's useful. Well, let me just take a particular picture here. I would say this is a picture from, I'm just using for demo.
What?
Wow, that's crazy.
I
Okay.
know.
Well, no, it's just one picture. It's not as high resolution, but I want to show you what a picture entails now, digitally. What it entails is, see these little boxes? Each box has a color value of red, green, and blue. Okay, now actually when you take the picture in a camera, it's not quite like that because we see green better than we see blue and red. And so they do funny things to take a picture, things like that. But anyway, when it gets down to the negative, in effect, you can think of it as there's a bunch of these little boxes. Okay, and at each box, if you see I have a little stopper here, if you look in the lower right-hand corner here, wherever I am, this tells you how much red there is, how much green, how much blue, it's some number. It's a number from 0 to 255. It's the computer math club, that's, the number you like, 256, 0 to 255. It gives you what the color is of that box, okay? So this is where mathematics with the modern age starts. You have, well, not quite, we'll be changing this. You have, each pixel has a certain color, and you can go in and see what's happening. Does that make sense? Okay, now, this is an old camera I had, an Nikon D200 or something like that, that I used with David Gillison, where we were taking pictures of the meat market and making big pans. This is an example of just one picture I took. I thought it was interesting because you have this model here. You have this model here, with the new way, the meat market. The meat market is down below 14th Street on the west side. It's really, hot now. It's like,
It has been for a while.
yeah, for a while. Well, we took these pictures as it was changing from an actual meat market to this hot place.
That must have been Juliana's time.
So here, this is stage quality deal, and here's the new person on the block, moving in over here. So this was the point of this type of a picture. But what I wanted to illustrate here is that really, when you get down to it, it's a bunch of pixels. And at each pixel, there's an RGB value, and now you want to manipulate it to get better results, okay? If you have film, it comes in as grainy and pictures like that. You can scan it to get into this sort of thing, but it's much easier if you just start with digital. But in any case, let me make this smaller. Okay, let me get that here. Oh, you see, by the way, I have 9 pictures of that picture. Because we'll be using this later on. This is a very simple example. The first picture I take is where I use an exposure that's very dark. And each one of these pictures gets lighter and lighter. Okay? All the way up to the 9th one, which is very bright. So I try to take them as quickly as I can. Actually, on this camera, I had something where it could do a burst and could change the exposures automatically. And then the point is you can put it together, because the thing is when it's too light, you miss some things because they blow out. It's so light you can't see any difference. Does that make sense? You see this light picture? When it's very dark, though, you'll see stuff that's really light, and you'll see what's happening. And when you look at a scene, you sort of look around, and your brain puts it all together. And when you're looking at the light things, your eye closes down, and you can see the bright things. When you look at the dark things, your eye opens up, and your eye changes, and you can see the dark things. So how can we do that with a photograph? Well, at least with 9 photographs. Well, that's what this was about. In any case, let me put it down here. Let me bring this back up to what we're doing. Okay. In any case, you get a camera. Basically, you have all these pixels. Then you've got to store it on a computer. There's a whole theory about how you store things on a computer. You've probably heard of JPEGs and TIFFs, right? Well, the difference is that a TIFF is not lossy. You don't lose anything with the TIFF. With a JPEG, what they're doing is they're going to lose some information but make it good enough. Okay? So the JPEG is pretty good. They use all sorts of mathematics, which I'm not going to get into. To do this, they use Fourier analysis. They use something called runtime encoding, which is fairly simple. What happens is that life is typically pretty boring. Okay? So you really, if you measure the difference from instance to instance, there's not too much happening. Except every once in a while, right? Okay? So you measure where you start from, and then you measure differences. Does that make sense? And it'll be small, so you don't need much information to figure out what that is. Does that make any sense? And so that's one way of compressing your life, or compressing a photograph. Just by looking at big things that happen, and then everything else, it's what it was before. What's happening? Nothing new. So that's how you compress a photograph, okay? But there are other things, you can do that and not lose any information, but you can do it and lose some information, you make things smaller. So if you take things in JPEG, the one disadvantage is if you keep on manipulating it and saving it, it'll degenerate after a while, okay? Whereas a TIFF, you keep on taking the image and playing with it, and it'll remain at the highest quality, okay? So now, once you have a picture like this, let's go back and look at these pictures. Where was I? VL9. Let's look at VL9 and VL5. I think I have VL5 and VL9. Okay, let's look at VL5. You can look at some mathematics here that turns out to be important. For instance, you can look at histograms. Let's see. Where is the histogram? Actually, it's in here. Well, let's look at levels. And then we'll see a bigger histogram. Anyway, the histogram is that thing in the middle. Now, it puts R, G, and V together. That's a little confusing, what that means. So just think of it as gray levels. What a histogram is a count of how many levels you have at 30. How many pixels are at the 30 level? How many pixels are at the 60 level? Does that make sense? Yeah. Okay. So in other words, here on the left, it's how many pixels are at 0. How many pixels are at 255? Notice there's a bunch of pixels. All of a sudden there's a spike at 255, right? Well, this is called a histogram. Probability does the same thing. If you're going to take a probability course, you create histograms. And they're totally related to probability. The probability you have a certain level of intensity, okay? And that it's like you make a histogram of grades in your class, right? How many people got a 30? How many people got a 70, right? You want to look at that, and then you can tell something about your class, okay? You can't tell everything about your class, right? But you can tell something about your class. You can tell something about your photograph. For instance, here's a histogram of this picture, which is sort of in the middle of my range of things. And, okay, let's look at a dark one. Let's look at a dark one. You'll see a difference. You see what's happening? That when you have a dark one, most of your levels are down near zero. Does that make sense? So, this is the beginning how mathematics can show you things, yeah?
So the graph is from 0 to 100?
0 to 255 here. Sometimes it'll go to 1 instead of 255. But it's 255 because you have that many levels, 256 levels of color in 8 bits of levels. Okay, now later on there are other formats that have many more levels of color. That's when you get to high dynamic range because we see more than that. It's not how C, because what's happening is that you could have 256 breaking up any number of intensities, but then you'll get something called posterization. See, posterization is when you don't have enough different levels. I'll show you. Let me show you what posterization is. I appreciate you asking about it. Okay, here's a decent picture, but let me posterize it. Okay, where is it? Posterize. With 4 levels. Okay, this comes from when you make posters. Okay, so I posterized it with 4 levels, and if you look at it, actually it'll look a little weird. They don't get it quite right. You see, you only have 4 different levels of color, of intensity, and you get artifacts. You get artifacts popping up. It's sort of weird, but sometimes you use that for effects. You see what's happening here? Okay? So in other words, now if I make just 2 of them, I'll just have black and white. Like if I posterize it, to 2 here. Well, it's not just black and white because we have red and no red, and yellow and no red, no yellow and blue blue is what's going on. Okay? So it's not black and white unless I made it black and white. Does that make sense? So, but this is what used to happen when people would make posters. That's why it's posterized, because you wouldn't have enough money to have all the colors, intensities, so you make it with just a few things and a few dots. So this is what happens here. It's related to this histogram. Does that make sense? And, let me go back to where we were here. Where is my history? Whoops, where is my history? I'm going to need to use this later on. Here, here's my history level. I can go back to what it was. Okay, this is Photoshop I'm using actually. It's a major image processing software that does all the numerical things for you. It's always changing. It's sort of like a tortoise, a big tortoise, because there are other new things that are coming out that do things better than Photoshop. But Photoshop keeps on getting better and better and absorbing everybody. It's a very hungry tortoise, if you wish. All right, so let's go on. So, we have these histograms. Let me get this thing up here again. Okay. Now, one thing you can do with a photo is you can make it bigger. Notice how I blew it up, right? You can move it around. You can rotate it. Now, all these things are mathematics. I don't want to go into too much about them, but they're not so trivial with photographs. Because how do you blow it up? In other words, you've got so many pixels. How do you make it bigger? How would you make it bigger? You would make the pixels bigger is the most simple way, right? Make each pixel bigger, but you can't make the pixels bigger, really. What you have to do is duplicate them. Does that make sense? So you have more of the same type, and that makes everything bigger. That's one way. But then there are more subtle ways of doing it, okay? Which they're called interpolating methods, okay? And I don't want to go into that. That's a whole topic. But don't want to cover it today because it would take me the rest of the lecture to really make it clear to you what's going on. Rotating. You know, suppose you think of rotating it. Well, the trouble is everything is lined up in a nice grid. When you rotate it, it's not lined up anymore, right? So somehow, and this is the same thing with scaling, you've got to take what you have and interpolate it to the rectangular grid. Does that make sense? It's got to be something called interpolation. It's called bilinear interpolation is the sort of standard thing. And this is what you do also when you want to make a picture have more pixels. You guess what you need, okay? You have to guess, and it's a mathematical guess, okay? So these things are all interesting concepts. Now, another thing that happens is you take derivatives on pictures. Take derivatives. What's a derivative?
How would you do that?
Okay, what's a derivative? Let me show you what a derivative is, okay? Okay, mass and derivatives. I have a picture of the derivative, and I'll do it, okay? You can also take integrals.
What?
Well, let me show you whatever, okay, but it's not going to be a real hard concept, okay? The thing is that there's a concept of a mask. And what a mask is that, you see this central part here, the central thing? This is your image. And then you're going to enhance the image. I'm going to do this. I'm going to actually do it on an image so you'll see what's happening. What you do is, you see there are all these numbers. The numbers are here, W1, W2. Can you read that? W, probably not. Let's see if I can get it bigger.
Yeah.
Okay. Oh no, it's Z1.
Oh,
Yeah, Z1 here. This is the image. It's Z1, Z2, Z3, and then here's the mask. W1, W2, W. The same. Each one of these matches up with here. Now a mask, you make a new value at the center of this thing. That's just going to be the sum. Whoops. That's just going to be the. Why is it doing that? The sum of the mask values times what's underneath the mask. Does that make any sense? I'll show you in a second how it's used. All right? Okay. So, and that's going to be your new value, and you do this at every point on the image. Seems like a lot of work, right? I mean, you have, an 8K by 8K image, that's 64 megs. That's a lot of pixels. Okay, you can have you certainly can have a 12 meg picture. Your cell phone has 12 megs. That's 12 million about. It's not really, it's a meg. 12 million pixels. And what it's going to do is it's going to take a mask like this and put it around every pixel and calculate this sum. Okay, now let me do it with a particular sum, which is actually a derivative. Okay, let me do a derivative. Okay, now watch what I'm going to do. All right, and let's see if we can. Okay, so here's our veal. Okay, here's our veal. I'm going to say filter. I'm going to say other. And I'm going to do custom. And this is actually, what I have here is a second derivative. It's actually what we call a Laplacian. Okay. Whoops. Minus 1.
So these are your z values.
Let me just tell you, okay. Now, let me do it here, and then we'll have to do something with the histogram.
Can you increase upon? By any chance?
Of this?
Yeah.
I don't know, let me see. I don't know if that's a good question. I don't know if I'll be able to do that. I don't think I can increase it. But I have a 1 here and a -1 here. What this means is that you're going to take, to figure out your value here, you take what's over here and subtract to the right of it and subtract what's to the left of it. you're looking at what we say is the difference in our picture between the left and the right. Does that make sense? Okay, that's a derivative. You know, if you do that and divide by the distance, that's a derivative. Well, the distance is very small here. You've got millions of these pixels, right? So this is a derivative. Okay, you're dividing by 1, but it's basically a derivative. And, okay, now you don't see much, but let me look at the histogram, because the histogram is, and then we'll play with it a little bit. See, the histogram is all over here. All right, so it's all dark, so you don't see it. But you can, your computer, if you did a processing, I'm going to spread it out. What this thing does is it spreads out the histogram, all right, so you can see it. So this is just what we got here. And do you see what's happening here?
Oh, that's cool.
We're getting the vertical lines.
Oh.
The point is that when you have a vertical line, the difference between what's on your left and what's on your right is greater. And also when you have sort of dirt like the bricks, you get lines. Okay, because the derivative tells you when things change. And what happens is that when you come to a line, things change. You know, you have a sort of general surface. Of course, the brick is not like that, but if we look at the faces or the designs on her shirt here, right? You know, the designs pop out because that's where you get a change from left to right. Okay, and the derivative is telling you, and this is the derivative. And you get your motivation of what to use from the derivatives. Yeah.
Is there also like a filter that actually does that automatically? That kind of does the same.
Yeah, you call it sharpen.
Sharpen. No,
But that's all based on this. I wanted to use the custom thing because it's, you know, people have made a lot of money making the best filters possible.
Yeah.
Okay, you know, because and what they do is they look at the mathematics and, you know, what you expect from mathematics, and then they use that sort of thing. In other words, why did I go 1 and -1 and leave the thing in the middle alone? Well, the reason is Taylor series. Okay, the reason is Taylor series. Let's see, where is my Taylor series? Let's go back to my, we use Taylor series. I did this in Maple. If you haven't had calculus, don't get upset. If you have a function, now we have, this image is just a function. Just think of the black and white. We have it as a derivative plus a second derivative plus something that's small. Okay? This is technical here. Sorry. If we subtract, we go a little bit in x and we subtract a little bit away. So you think of this as being around 0. A little way x and a little bit at -x. What happens is that you get 2 times the derivative at 0. It gives you the derivative at 0 nicely. In other words, you'll find, and you don't even get the square term. It gets rid of the square term. It's a better way of getting the derivative than if you just take f of x plus 1 minus f of x. Or f of x minus f of 0 is what it would be here. And the same thing for the second derivative. If you do something like this, you'll get the second derivative. Okay, let me do that. Let me show you the difference in the picture. Let me do one more thing. And you know, you're not going to understand this now. Let's go back to the beginning here. And let me make another filter. Let me make another filter. Custom, and now I'm going to make here this be, what was it, 1 or 2? 1. I have an appointment. 1, 1, 1, and -4. I think this was the right thing. Let me just see now. I'll do the levels again. This actually turns out in general to be better. Okay. and we even get a better picture of everywhere where there's a big change. And this is motivated from your 176, if you take 176 with Taylor series. Okay? So those of you in my 156 class, I'm going to teach you this.
What?
Okay, to let you know what Taylor series will help you do with numerical analysis and motivate you in some form of image processing. All right? Question? Okay, I mean, there's a lot of technical stuff here I'm not going to go into right now. You know, I have to really work on it and tell you what's going on. But basically, when you take f of x plus 1 minus f of x minus 1, basically, you're taking a derivative. Okay? Yeah, question?
I just have a question. So how did you start like with the numbers because to be able to do the derivative you need to know like the distance. So how do you?
Well, the distance is going to be the resolution of the pixels.
Alright, so
Right? So if you have a more resolution, you're getting more and more like a derivative. Right? So in other words, if you have a camera that has 24 megapixels, it'll be even more like a derivative. Okay? So the derivative is when you have delta x from one to another, right? Well, here we have one more pixel, but the one more pixel is really close.
So
Right?
it would be the pixel, that's what you're saying?
Yeah, the pixel is the delta x.
Alright.
Okay, now we're not dividing by delta x, so we don't get a true derivative, but it gives you the magnitude, relative magnitudes of the derivative.
I see what you're
Okay? And so you motivate yourself by understanding what a derivative is. Okay? All right. So now let's look at another thing here. Let me go back to the original. Where did oh, where is it go? Okay. There's another thing where you want to blur a picture. You often want to blur a picture. Okay? And actually, if you blur a picture, you can then use it to sharpen a picture. What is blurring of a picture? How do you blur a picture? Well, what you do is you take an average. Okay, you use a mask that takes an average. Okay, let me show you what a mask would be to blur. Now, actually, they have these, they don't have to be custom, but if you take 1, 1, 1, 1, 1, all these ones, okay, and that's, how many ones? 9 of them, and we're going to take a 9 here, okay. What this does, what this mask does, is it around every point, it adds up the 9 pixels around the point. Does that make sense?
Yeah.
And divides by 9. What's that doing? It's taking an average. Around every point, it takes the average. Well, that's really an integral. If you look at it correctly, it's 1/9 times the value here plus 1/9 times the value there. That's how you take an integral. And then you get a blurred picture. Let me see if I can show it to you, how it's blurring. Okay, here's after, here's before. Can you see the difference?
Yeah.
You know, before, after, blur. If I used more space to average, I'd get more of a blur. Okay? And you can also sharpen by adding in edges. So they have sharpening masks where you take derivatives to get the edges and you add them in. Does that make sense? Okay, so, you know, here's sort of your basic math that's, you know, you learn in calculus that motivates all these derivatives and integrals and things like that. They're used at this basic type of image processing level, and photographers use this all the time when they're manipulating images. Okay? And then the idea is also, I won't go into it, there's a way you can use blurring to sharpen.
I know.
What?
Yeah.
You can use, it's called an unsharp mask.
Yeah.
Okay?
I've used it.
The point is that, you know, well, I have a little diagram here that, you're not going to understand it this quickly. I'm sorry, I'm trying to do too much, of course, I always do. But I have a picture here, an unsharp mask. You see what happens is you have your original signal, and then you get an approximation to the original signal. So the original signal is this something that's got all these edges and stuff, right? And then you blur it, and the blurring thing is this sort of curvy thing. Does that make sense? Mm-hmm. And if you subtract the blur from the original signal, you're going to get bumps, because most things are the same. You'll get 0. You subtract the blurring things from areas where it doesn't change, you get 0. Does that make sense? If you blur things and you're in an area where you don't change, the blur is the same as what you are, right? So you subtract the blur and you'll get only bumps where things change. Does that make sense? Then you add that back to the original picture. And so that means that it'll enhance where there's changes. Does that make sense? So that's called an unsharp mask. This was used in film photography when they had a darkroom. They'd actually put a blurred picture of the photograph or something to blur it. That this sort of added the subtraction of the blur to it. It was used by photographers for years before it became digital, this unsharp mask. So, these things there are all these things. Okay, let's go on. Next thing you might want to do is combine images. Okay? Like, for instance, I don't know, I'm going to run out of time here. If you have all these Veal things at different exposures, you can put them together and get one thing that has all the exposures in it. Okay? Now, the trouble is you can't display it. The displays are not good enough to get all those values. Actually, you go to a big conference, they have all sorts of devices to try to get more dynamic range, they call it. Okay? But you can store it, and then you can manipulate it to get something that's more colorful. Because you have all the range, you can play with it. So I did it, I'm not going to have, you see, like, this is about the best picture we have of, well, actually, this one is okay, I have that just what you would take with the camera. This is exposed right. If you put them all together, I don't think I have time to show you how you put them together, but maybe I'll do it with a pan. This is, okay, let's open the image. This is the same picture after I've used 9 shots and done as best I can to, let's see, where's Veal 5? Oh, here it is. Let's look at the, okay, you see that one versus, oops,
The last one.
this one. Okay, this one, maybe the woman next to her is even better. Okay, there's a woman
Yeah,
next to
notice
her.
that one.
Yeah, you didn't even notice her here. She's very dark. But the point is that you can bring everything out. She's really mysterious, and you'll see it when you look at the shot, because you look here and your eyes adjust, you look there, your eyes adjust, and you see much more dynamic range than the normal camera will have. But you can put these photos together to get this. Okay, now, I won't show you the process, but part of the process is matching the photos up. In other words, you have to try to figure out, you have to put them exactly on top of one another. Now, you can do it with negatives and stuff, but it's very hard. Mathematically, how do you match them up? And what that corresponds to is finding very important points, that you make some definition of what an important point is, and then matching those points so you can move the things on top of each other. For this sort of thing, with different exposures, I took them on a tripod, And when you take it on a tripod, they're going to match pretty well to begin with. Does that make sense? But it still has to do some work. But nowadays, you do this on your cell phone camera, it'll still match them up. It has all that software in a good cell phone. Okay, this is called HDR. It actually does it automatically for you. It does it with 3 shots typically now. It'll get to be 9 shots or whatever it needs. 9 shots is, you never really want to go more than that because it gets out of control when you try it. But let me give you another place where you need to match it up is with pans. Let me give you a night shot. Okay. And here I've taken 30 shots. Let's see, I'll give you, each shot looks something like this. Whoops, where is this? Okay, let's make it bigger. You know, each shot looks something like this, and there's lots of these shots up and down. This was taken on, David Gillison and I, as I said, we're doing these shots of Lower Manhattan near the meat market, and this was on the top of his building in Westbeth, it's called. It used to be the Bell Labs years ago. But anyway, there are about 30 shots, put it together with software, and you get something like this. Let's get it here.
Oh, that's awesome.
Do I have the whole thing? Let me just see. Okay, here's the
It's
thing.
like, what do you call that thing?
A pan.
Yeah.
A pan. Okay.
Cool.
So here's this pan. And this was only with an 8 megapixel camera at the time.
You joke.
That's what it had at the time.
Oh
But
my
this is
God.
30 shots put together. You see, and then processed. Now, you know, it's you know, there's the Statue of Liberty.
Oh my god.
You know, but it also actually it wasn't just 30 shots. This was 30 shots. For each shot, I took 9 shots for different levels of light. Actually, I only used 3 at the end. In the dark, you didn't need that many. So in other words, I was doing HDR and then making a pan. Okay? And so, but all of this depends on being able to match up points in different photographs. I'll do this right now for you. I mean, I'll show you the process because I want to show you what it has to go through. Let me get Autopanic Giga 4.2. Okay. And let me show you, it's on this machine it goes really fast. When I did this, they didn't put them together that well. You had to go in with your hands and move them around so they get on top of each other. You had to correct things. It took me weeks to do this. Let's get this bigger here. And let me get the photos in. Select images. Alright, I want to select these 30 images or so. By the way, these are after they were processed for light. Okay, see, it just takes them in. It's very fast. You can do this in Photoshop, but it's very slow. Did I push that button? I guess I pushed the button. Okay, here it's getting it together. Let me just show you a process. You can do this in Photoshop too. This is a particular piece of software that's very fast. You get something like this. Let me edit it.
Is it free?
No.
No.
Definitely not.
Expensive.
Okay. Now the thing is, when you get it, this is a problem you have on your cell phones too. It makes it tries to get everything you took in there, and it projects it. It's not a perspective projection. Okay, you'll find that typically you'll take a pan with your cell phone, you'll get these curvy lines. This isn't what my picture looked like, right? Mm-hmm. You get these curvy lines like this and stuff like that, because what they have to do is they're taking something that you can think of on a sphere, okay, and then they have to put it on a flat piece of paper. Okay, now you know the globe doesn't work well when you try to make the projections on a flat piece of paper. You have all these different possible projections you can use. This is too small. You know, you can use spherical, planar, cylindrical, Mercator. Mercator is what you do on maps. Okay, this is where math comes in too, where you have to project these things. How do you project these things? Does that make sense? So, for this, I didn't like that, but I wanted to get all the information because then I could take portions of it and I could play with it, all right? So, if you want it to be perspective is planar, okay?
Oh,
Perspective is planar. Well, that looks terrible,
yeah.
right? Well, then you've got to cut it down to size. In other words, you decide what's the region you want, okay? And so this is, you know, I'm not gonna, you know, this took weeks to do right, okay? And we start getting somewhat like what I had, okay? Does that make sense? This software is much better than what I was using years ago because, you know, this was done about 5 or 6 years ago, and the software has gotten better and better for this sort of thing. Let me just show you what they're doing also. What they're doing is, you see these, oops, see all those lines there? This means that this is one of the pictures is hooked into this other picture. They have to put all the pictures together. And actually it gets very complicated. If you take a picture here and then rotate your camera and take a picture here, you can't put it together just by going like this and like this. There's linear algebra involved to put them together. It's called a homography, big word. Okay, but it's got to be distorted in a certain way to match with a perspective projection. And that's all done in here. And for any two pictures, you have to find points in one picture, well, that's the green points here, and they have numbers that correspond to points in the other. And how does it find points? That's really mathematical, okay? You have to find points where it can recognize this point goes with that point. Okay, you got all these windows, great, they all look the same in the corners, right? You know, there may be subtle differences. Well, this is where all these derivatives and math and linear algebra come into play. Does that make sense? Okay. So I don't think I think I'm running out of time rapidly here. I also was going to show, but I think I won't. You can take many pictures and make them come together and make everything in focus. All right. Let me show you though a new concept that takes all these concepts, the litro. Okay. This is called a litro. And let's look at this picture on the left. Okay. Now, the couple is out of focus. All right. If I click here, let's go like, let's see, what do I want to do here? If I click here, they'll come in focus. If I click here, that'll come in focus. Do you see? Can you see that?
Mm-hmm.
If I click over here, that'll come in focus. Okay. Now this is one shot. This is one shot. This camera with one shot can take a picture that you can then change what's your focus. You can also.
I think we have that from
You can start
Instagram
doing
too.
that with your phones now.
Right.
You can start like
right.
you take
Yeah.
a picture and
These
you can
guys
just
have been
take it.
hired
Yeah.
by. These guys have been hired. Well, you can choose the focus when you're taking the picture.
Yeah, but afterwards
Yeah,
you
after,
can do it
right.
too.
Yeah.
They're all getting this sort of thing.
Yeah.
His thesis advisor was hired by, I think, by Microsoft. He went to Google. I don't know who Apple took. These guys were all at Stanford who did this sort of stuff. And
So Apple just randomly did it.
they didn't randomly do it. This has been researched for many years.
So wait, so
And basically,
they stole it anyway.
everybody's using it. It's been out there.
Oh, okay.
The concept is to have like an insect eye. Instead of one lens, you have a lot of little lenses. And because of that, you can get what's called a light field. You don't no longer just get an exposure at a different pixel. You get this whole field of light. And because of that, you can refocus. You can also change your point of view. I don't know if this one will let me do it. You can actually change your point of view. In other words, as if you were standing over here.
That's
okay?
crazy.
And it's because you're using sort of a lot of little lenses. The trouble with it is that it needs a lot of light. You probably find in your cell phones too, that if it's a little dark, this won't work at all, right? That's the problem, because it's again getting to the pinhole camera concept, where you have little holes, you get it all focused, but here you have lots of little holes, so you can focus it anywhere you want. And the mathematics involved in here is really immense. It gets into the same mathematics you use for CAT scans, things like that. It gets into all sorts of
Your cell phone.
yeah. Oh, yeah. These are made much more powerful computers than when I first got computers for this.
Was in like
It's my
was in the
dad's favorite
first
subject.
Huh?
It's my dad's favorite thing. I'm holding my hand a computer that's more powerful than anything. He's talked about how he's holding in his hand a computer that's more powerful than giant rooms that he
Yeah,
uses.
yeah. I mean, you have what? I don't know how much memory you have now. 2 gigs of memory in your cell phone. I mean,
Yeah.
They're
Right.
putting
I
4
mean, I
now.
remember when I got.
They're putting 4 now.
I know. I got
Yeah.
32K. When I first got a computer, the Apple II had 32K, and you can put it up to 48K, and so
Not
you had
even
more
a
room.
download a movie like in a couple minutes. and
Yeah,
stuff.
I mean,
Yeah.
it's, that's, the cell phones are, I don't know what's gonna happen to our big cameras.
They're
You know,
a supercomputer.
Yeah, they're turning into supercomputers. You've got this supercomputer. Eventually, maybe they'll put it in us. I suspect we'll lose our appendix and we'll have everything there, Yeah.
I mean, I was recently, we probably know more about it. It's like, right now the next, like 5G, it's supposedly gonna be like so fast that you can download something that's like a couple gigabytes in seconds.
Sure.
I was like, I can't believe this. When this happens, I'm just gonna be like
Well,
flabbergasted. Like,
look, I
it's
have
gonna be,
all my photographs. I have them on, like 12 gig, 6 gigabyte dual drives, so I don't lose them. And I have a backup I put in my office in case I get wet or something there.
Loud back.
It's all going to be on the cloud,
Yeah.
right? With all this stuff. Of course, what's going to happen is that the warfare will be destroy the other person's cloud. Right? Everything's up in the
Our
cloud.
database got bombed.
Everything's in the cloud, so everybody will try to destroy everybody else's cloud is what's going to happen. But anyway, you have this type of thing. And let me just show you also Snavely's thing, which again this is all made possible because you can, this isn't made possible from that. This is a whole concept of, a light field, which I don't have time to go into. And then, where am I here? I've lost my place where my stuff is. Oh, where to go? Oh, I know where. It was a web page away from this. Okay. Then we have this phototourism, which is what I told you about before. This is from 2000. I'll let him describe it.